Okay, so it is my distinct pleasure to introduce a longtime friend, Barbara Manganis Braun. We were classmates at MIT, partners in crime. My distinct pleasure. I need to pause the YouTube thing so that I'm getting two things with delay. Okay, try again. My distinct pleasure to introduce Barbara Manganis Braun, MIT classmate of mine, partner in crime, so to speak, and longtime friend. She graduated from MIT in 1995, was in the Air Force for a while, now works for the Aerospace Company, designing and building and implementing things relating to rockets and science and satellites, stuff like that. And she'll tell us all about it. So without further ado, Barbara.
Okay, I think I've remembered to unmute. I'm going to share my screen here. Once I figure out the best way to do this, let's do it that way. Okay, hopefully everybody can see the screen, and I'll try to keep looking at the screen and not at my little cheat sheet down here. I'm really happy to be here. Thank you, Jeff, for reaching out to me, Mr. Bigler. And I am happy to talk to you a little bit about rocket science and what I do. And the title is Rocket Science. It's not brain surgery, because even though rocket science is kind of complicated and there's a lot of work involved, really the underlying concepts aren't all that difficult. And so we're going to try to get through those. And hopefully by the end of this talk here, you will all be rocket scientists. And then it's just a matter of getting a job as a rocket scientist. And we'll talk a little bit about that too. So the president of my company, the Aerospace Corporation, she's a former president. She was Dr. Wanda Austin. She always said that she started out STEM talks with pictures of herself in high school, or pictures of herself at the age of the people that she was talking to. Now, I think she probably had a lot better pictures of herself in high school, but here's what I looked like when I was you. I grew up in Somerville. I went to high school in a place called Matignon High School. I think it's called the Cambridge Matignon School now. And I graduated in 1991. While I was in high school, I was part of the drama club. That's me wearing a wig, playing Audrey in Little Shop of Horrors down there. And I also was on the track team. And I wasn't very good at being on the track team, so I did high jump. And I wasn't very good at high jump either, but there were fewer people who did high jump than did, say, the 100-meter dash. So I could at least score some points for my team, at least by default, if there weren't enough high jumpers involved. So I did graduate. I did go to college. I got an aerospace engineering degree. I went to the military for a little while, and now I work for what's called a federally funded research and development corporation. It's a nonprofit corporation whose job really is to provide technical support and advice to space stuff, among other things. So I work with NASA, and I work with the military, and I work with universities and commercial companies doing essentially space stuff. So what made me want to be a, quote, rocket scientist here? Well, this is a picture of the 1997 explosion, sorry, the 1987 explosion of the Space Shuttle Challenger. And I was in 7th grade when this happened, and I was already sort of interested in science and engineering, but this is what made me want to be an aerospace engineer. And it's kind of odd. I kind of thought this was perhaps a little morbid on my part, but it turns out I wasn't the only one. A lot of people in my graduating class of aeronautics and astronautics majors also were inspired to become aerospace engineers due to the Challenger. And I think it's, you know, a little bit like what we're seeing today. I expect to see a lot of biochemists and epidemiologists graduating in the next few years after COVID. I think it's kind of speaks to us as humans that we like to solve the hard problems, or we're inspired to solve the problems that we see out there. And that's kind of true for what, you know, what I do and what I really enjoy doing. So what does a rocket scientist do? Well, this is perhaps my middle child, budding rocket scientist here. And he's launching a model rocket from the desert of New Mexico, probably about an hour from where I live. And, you know, you could call him a rocket scientist. But here is another video, slightly more spectacular, a lot more shaky video. My 10-year-olds took this
at
the Falcon Heavy launch in the summer of 2019, and I was working on this launch.
10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Flash.
Well, outside with everybody. One of the things you notice when you go to a rocket launch in person is that I can talk over it. It takes a while for the sound to reach you. So what you really kind of see is this silent star rising from the launch pad. And then, 10 or 15 so seconds later, the roar hits you, and that's pretty spectacular to see. Later on, we'll have a video, or not a video, a picture of the double landing that occurred. This was a mission called the STP-2 mission, which I'll talk a little bit more about later as we go through this presentation. One of the things that we had with that double landing was a quadruple sonic boom as the end stages of the rocket came back. Most of you probably have heard of SpaceX. They're the ones doing all the launches and all the fancy landings, and they just launched a bunch of astronauts to the space station, which was the first time in a long time that we've actually launched our own astronauts to the space station. So those are some of the ideas, some idea of what a rocket scientist does. And before I continue, I do have to confess, I'm not really a rocket scientist. I'm more of a satellite engineer. I don't do an awful lot of propulsion. I do a lot more of things that we put onto rockets. And that being said, I do a bit of figuring out how to get these things onto rockets, figuring out where they're going to go once they launch and so forth. So what do I do as a satellite or a spacecraft scientist, as engineer? Some of this stuff may be a little old. Some of these are Star Trek-y type things. This middle one here is probably, with the people around the satellite, is probably the closest thing to what I actually do. Down at the bottom here is a really cool science fiction series that you can try to find called Firefly, and that's sort of how I see myself. Of course, what I actually do is a lot more meetings, presentations, and arguments, basically trying to discuss and decide how to design something, trying to convince people that launching this satellite is a really good idea, trying to going and explaining your rationale for what you think is the right thing to do and the wrong thing to do, and trying to work out things like mission operations and what we do once the satellite actually gets on orbit. I do a good bit of satellite design and systems engineering, and we were talking about CubeSats before this presentation started, and I'll have a little view of a CubeSat here shortly. But I spend a lot of time trying to figure out how to pack everything you need for a satellite into a form factor like a very small CubeSat, or even like bigger satellites. We don't have crude oil or fireworks or spark plugs on our satellites, but we do have batteries, and we do have solar cells, and we do have radios and computers, and then whatever the experiment or the mission is that we actually need to use. So figuring out how to get all of those things into a small satellite or into even a bigger satellite, how they will all work together to do what the satellite needs to do. That's kind of what I do every day. I do a lot of analysis, and analysis, like I talked about before, helping people decide what decisions to make, whether to go with a bigger satellite or a smaller satellite, whether to launch it into one orbit or another orbit, or, in some cases, the actual decision making is harder to get to than the analysis. And so sometimes that leads to a lot of inefficiency, but I do enjoy the analysis. And one of the things that I do enjoy doing a lot that I'm going to talk about next is orbital dynamics. This has to do with how things in space travel and move and how the planets go around the sun. And so to talk about it, I figure, you know, I could stand here and describe it, but instead I'll play a few videos here. So we're going to kind of start here your 1 hour or maybe 30-minute education in being rocket scientists by talking about orbits. So this is the Earth. This is the International Space Station, and I'm going to play this as if you were sitting on maybe another satellite or on a long tether, looking down at the International Space Station as it's orbiting the Earth. Now, the International Space Station is in what we call low Earth orbit. It's about 220 miles or 400 kilometers above the Earth. And it is traveling the Earth such that it makes an circle around the Earth, an orbit around the Earth about once every 90 minutes. And we use these orbits for lots of different types of Earth missions, like Earth observation, like experimentation, some communication. We'll talk later about another type of orbit that we use a lot for communication. But recently, as you may have heard, the company called SpaceX is launching a lot of things called Starlink satellites. And these are developing essentially mesh networks around the Earth to provide internet to everywhere on the Earth. So that's a low Earth orbit, or the ISS orbit. Let's see, go on to the next one. There we go. This is a geosynchronous orbit. This red line that you see down underneath close to the Earth is the ISS orbit that we just looked at. And this is a geosynchronous orbit. It's a lot higher above the Earth. This is about 100 times higher, about 22,000 miles instead of 220 miles. And as you might guess from the name, this orbit is positioned at a distance from the Earth where it circles the Earth at the same rate as the Earth rotates. So if from the purposes of the viewpoint of the Earth, it stays in the same place on the equator all the time. So if you park a satellite into this orbit above the United States here, it will always be in that same spot above the United States. And this is where, for example, your dish TV and you know, any Sirius satellite radio and so forth, they tend to park themselves in this geosynchronous orbit about 22,000 miles above the Earth. And that way, when you're sitting there with your dish TV or a satellite dish on the roof of a building or on the roof of your house, you point it to one spot and it can stay there the whole time. So that's a pretty useful orbit too, used a lot of times for, again, communication, television, some weather observation, a lot of military satellites in geosynchronous orbit. It gives you a nice view of roughly half the Earth. So now we'll go on to kind of an interesting and a fun orbit, if I can figure out how to click to the next one. This is called a Molniya orbit. And this has got a tilt to the orbit that's about 63 degrees to the equator. And it's about half as high as a geosynchronous orbit in its semi-major axis, but it's a highly eccentric orbit. It's got a big difference between the farthest point from the Earth and the nearest point to the Earth. So when you watch it, this is what happens. It sits here and it's dwelling right now above Canada. But as we get closer and closer to the Earth, and I don't know that you'll get the full effect here, it's almost like riding a roller coaster. You're going to swing around the nearest point to the Earth, and then you're going to rise up over, you know, Northern Europe, Northern Russia, and so forth. And this is an interesting orbit because if, for example, you want to do communications, but you're in Northern Canada or Northern Russia, you can't get your antenna dish to point all the way down toward the equator. It's you're kind of blocked by the Earth at that height. So it's called a Molniya orbit, in fact, because the Russians use this for communications and for imagery instead of geosynchronous orbits. And the word Molniya actually means lightning in Russia. And it refers to how fast you tend to go down past that point that's closest to the Earth, called the perigee. So I'm going to do this one more time, and then we'll look at all three of these orbits together. So there's the Molniya orbit. Okay, so these are all the orbits that we looked at. Here's the ISS, really, really close to the Earth. Here's the geosynchronous, much farther out from the Earth. And here's the Molniya, and you can see it's not only tilted quite a lot compared to both of these other orbits. It's also got a big difference between the closest part of the Earth and the furthest part of the Earth, between what we call the perigee and the apogee. So here's the first step in becoming a rocket scientist, and this is Kepler's laws. And Kepler's laws are stated here as if they're around the sun, but it works around a planet too, and basically anything that has enough gravity to have something in orbit around it. What it says is, the first one says that the orbit of a planet, or in this case, a satellite, is an ellipse, and a circular orbit is just a degenerate case of an ellipse, is what we would call it. It's just a very not interesting ellipse. But it's an ellipse with one of the foci, and when you take geometry, you'll understand a little more about conic sections and ellipses. One of the foci is the planet or the sun that you're going around. So every orbit, if it's a circular orbit, the sun or the planet will be right in the center. If it's an elliptical orbit, there's a spot here, and then there's another spot a little bit kind of reflected like this on the other side. The thing that you are orbiting will be in the center of that, the sun, or in our case, when we're talking about satellites, the Earth. So the other thing that just explains why the Molniya orbit behaves the way it does is that the second of Kepler's laws states that the area that is swept out by a satellite moving through space for a certain period of time is equal all the way around. So in other words, if you're closer to the sun, this distance between the sun and where your planet is smaller, so it'll go faster through the period of time that takes you, I'm going to go back now, hang on. There, that takes you from this beginning of the time to the end of the time. So this 1 month goes faster here, or the Earth goes further around the sun when it's closer to the sun in 1 month than it is far away. So the Molniya orbit, where you've got a really close perigee and a really far apogee, that close perigee, the satellite kind of zips through that like lightning, and then it comes way out to the apogee, and it spends a long time out there, and that's all due to Kepler's second law. And then Kepler's third law states that the square of a period, the time it takes the orbit to go completely around once, is called the period, that the length of that time is proportional, or the square of the length of that time is proportional to the cube of the length of the semi-major axis, which if the orbit is circular is equal to basically the radius of the orbit. And if the orbit is elliptical, it's basically equal to the radius essentially of the center of this, the longer side of this. So that is why if you want to make your satellite go around the Earth at the same rate that the Earth spins, you want a period of 24 hours. And if you do Kepler's laws or Kepler's equations, you discover that that number is 22,236 miles. So that's the first half. You're about halfway to being a rocket scientist there with Kepler's laws. So here's another type of orbit, and we're going to talk a bit about what we do with satellites in these types of orbits. This orbit is called the Sun Synchronous Orbit, and it's an orbit of a satellite called CubeSat that I work with a lot. This is a type of low Earth orbit, and there are two things that are kind of useful around this orbit. We're looking at the Earth as if we were sitting on the sun with a very large telescope. And what we would see if we played the simulation out for all the way through the year is that the angle of this orbit to the sun never changes. Or if you put this another way, if you were standing on the equator anywhere in the world and it is 1:30 in the afternoon, this satellite is coming overhead. And as it comes overhead, the Earth rotates underneath it, and then pretty soon it's 1:30 in the afternoon. We call that a mean local time. Anytime these satellites pass overhead. That means that you get to look at the Earth with the same lighting conditions, which can be pretty important if you're doing Earth observations or taking pictures of the land or something. The other thing that's useful about this type of orbit is you can see here, this satellite here has if this satellite had an instrument, and as I'm playing this, it's essentially taking pictures. As the satellite goes around the Earth rotates underneath the satellite, and in the course of one day, you can pretty much cover the entire Earth. And these are sometimes called polar satellites because they do orbit near, if not exactly over the poles. And this is the orbit of a satellite, like I said, that I work with, that's called CubeSat. And this is a cute animation of CloudSat. CloudSat looks at, you might have guessed, wait for it, clouds. And it's in one of these sun synchronous orbits. And so it orbits the Earth 14 or 15 times a day, and it takes pictures of the vertical structure of clouds. So you can see here, it's not only looking at just the top of the clouds like your basic weather satellites, it's also looking down through the clouds. And this is over a typhoon called U2 that was in the Pacific in 2018. It looks down and it's actually measuring the raindrop intensity all the way from the top of the clouds through the Earth. So a lot of these sun synchronous or polar orbiting satellites are useful for Earth observation and Earth imagery. And CloudSat is one of those. Let's see if I can get this to just advance. Here is a picture of CloudSat. It's a pretty typical satellite. It's probably a little smaller than the average of all the satellites launched since the 1980s or so, at about 700 kilograms, or at 1,500 pounds. You can see the people here working on it. And along the spectrum of satellites, it's probably about weighs as much, a little more than a grand piano, but not quite as much as a Volkswagen Bug. But as we were talking a little bit before the presentation started, up until now, or up until probably about 10 or 15 years ago, most of our satellites were in this upper half of the graph here, where they were, along the side. The biggest of them were maybe the size of a pickup truck or even a small bus. And many of them were in this middle age where they're somewhere around a VW Bug or a grand piano or something. But nowadays we have satellites that are a lot smaller. And in particular, I'm going to talk a little bit about CubeSats. So CubeSats are kind of what they sound like. They're small satellites shaped like cubes. And I can't actually see my own video here, so I'm going to try to remember to hold this in front of me so it doesn't get lost in my virtual background. It's maybe a little bit bigger than a Rubik's Cube. It's about 10 centimeters on either side. And they were invented about 15 years ago by a couple of guys, Bob Twiggs and a gentleman known as Jordi Puig-Suari. And they wanted to give their students, their college students, a platform so that they could launch into space and put a bunch of instruments on just for experimentation and to learn how to build satellites. So they were kind of thought of as fun things for research and development missions. But because they're super easy to launch, and we'll talk about that here, they've become so popular that governments and commercial companies are starting to build them and launch them. So you can have one that looks like this, which is called a 1U satellite, and you can stack them together. And over here I have just a 3D printout. This is a 3U satellite. The U is a unit. So you can make a satellite as small as this, or you could kind of make a satellite that is about the same size and shape as 3 of these stacked together, or you can make them as a 6U or as a 12U, or even up to a 24U. And just like, in the 1970s or so, you had to have a computer about the size of a room to do the same sort of, that had the same sort of computing power as something that you carry around on your iPad or on your phone. Back in the 1990s, we would launch satellites like Terra, which is in this, another NASA Earth observation satellite that's in this lower picture. Now these little 1U, these little 10 centimeter square CubeSat boxes can do a lot of, maybe not all of, but a lot of the same sort of things. But the trick is getting these all to space. And this is what kind of makes CubeSats useful, is because you can take them and put them into, this is a CubeSat deployer. This is an actual CubeSat deployer. This is an actual CubeSat, but it doesn't have anything in it. So it's kind of like a model. But these deployers here are a bit like a jack in the box. And so you put it's got a big spring in them. And so you put the CubeSat in. And then you close the door. And you put this onto something that's going to the space station, or on the left-hand side of this picture is the STP-2 mission again. And we had about 12 CubeSats on this mission. And then when you get to space, you push a button and it releases this, and the CubeSat literally is pushed out, or you can stack 3 of them together and push them out. And that's exactly what you see over here. This is something on the ISS, on their robotic arm. They load the CubeSats up here. The astronauts will just take this and load it onto the either the robotic arm will come and pull it out of a cargo resupply mission, or the astronauts will load this up and push it out in an airlock, and they'll deploy these CubeSats into orbit around space. So getting all of these things to space, and part of what makes it so attractive to so many people is that it's pretty easy to find room on a big giant rocket launch for something as small as this. And as a result, there are a lot of opportunities to launch these things. And so just like we're moving from these big satellites to these really small satellites in the past, where we would put a big satellite, maybe one or two, into a giant rocket like this and launch that into space. Now we're putting more and more of these smaller satellites. And in the case of the STP-2 mission, we put about 12 CubeSats and about 12 slightly bigger than CubeSats, but smaller than CloudSat satellites onto this single rocket, and we launched that into space. And I spent a lot of time doing that, figuring out how to put all of these things together and launch them up into space, and making sure that everybody from a university to a government laboratory to a military agency to a foreign company to a commercial company can all work together on that. Okay, so once we get them all on the rockets, now we'll get on to the actual rocket science and talk about how we get them to launch. So like I mentioned, it can be tricky. It's sometimes tough. It's hard to get all these things to play together, but we've got it's a really exciting time to be a rocket scientist, because we've got a lot of people building rockets. We've got companies like SpaceX that are doing the Falcon. We've got companies like one called Rocket Lab, which was actually founded in New Zealand, but now builds rockets. And they build really small rockets designed to launch these smaller satellites. We've got companies like Virgin Atlantic, which typically you think of as an airplane company. They've got a subsidiary now that's called Virgin Orbit, and they just launched a rocket that literally attaches to the underside of an airplane. And the airplane takes off from a regular airport or a military base, flies out and drops that rocket, which then ignites and goes off into space. And of course, we have the space station, which likes to have people bring satellites up to the space station and then get deployed off of the space station. A lot of CubeSats are deployed that way. So how do you get there? So this is a thought experiment called Newton's Cannonball, which some of you may have heard about. And the basic premise is, if you shot a cannonball or a bullet straight out horizontally from where you're standing, it would travel a certain distance and gravity would pull it back to Earth eventually. So it would go a certain amount of distance away before it dropped to the ground. If you launch something bigger, like an intercontinental ballistic missile, it would travel a much further distance before gravity finally pulled it down to the ground. But if you launch a big enough missile or a big enough rocket, and one of the things that I have worked on is turning old intercontinental ballistic missiles into rockets to launch satellites into space, which I think is kind of cool, and a cool use of this sort of Cold War era technology. But if you launch something big enough, it will go fast enough and far enough that eventually the Earth's curvature will fall away as you are falling toward Earth. And you're essentially going to enter into orbit, or you're going to basically throw yourself at the ground and miss, for anybody who has read The Hitchhiker's Guide to the Galaxy. So just to point out while we're on this here, the concept of zero gravity in space is a little bit of a misnomer. There is gravity in space. That's what keeps you in orbit, because if you didn't have the Earth here and its gravity to kind of curve your path around, you just fly off into interstellar space and never return. But they are in essentially free fall. They're just continuously throwing themselves at the ground and missing. And because of that, it's like being in an airplane that takes a sudden nosedive. You essentially experience that lack of gravity or that weightlessness as the ground falls out underneath you. Okay, so this is the second part of being a rocket scientist. And this is how we actually figure out how much it's going to take to throw ourselves at the ground and miss effectively. For those of you who've taken some physics, the system at the right here has a certain momentum, and the system at the system on the left has a certain momentum, and the system on the right, which is at a time a little bit later than the system on the left, has the same amount of momentum. For right now, just like all good physicists, we're ignoring drag and other other forces that are external to this system. So physics tells us that the momentum of the first system has got to be equal to the momentum of the second system if there are no external forces. So at the beginning here, you've got this mass and this delta mass, that's your fuel, all moving at a certain velocity. If you throw a piece of mass out the back of your rocket at a very high velocity, then you'll add a little bit of momentum to your rocket, a smaller amount, because this is a much bigger mass than down here. Now, this is all pretty straightforward, and you could write an equation and solve for all of this, except for one fact, which is as you take a little small piece of mass here and throw it out the back, you're lightening this mass. And so you need some calculus, but at the end, you end up with basically these equations that say the amount of delta V, the amount of change of velocity that you get, is equal to the speed at which you are throwing mass out the back of your rocket, times the natural logarithm of the initial mass over the final mass. And I promise that's the last equation in my presentation. But this is essentially how you figure out if you've got enough fuel to get into space. And it's also how you figure out that, for example, most of the mass of a rocket is fuel. And in fact, it's very efficient to, once you're finished with the fuel in one fuel tank, to eject it and to just move on with a much smaller mass. And that's why we have things like the first stage of a rocket, which when the fuel in that has burned up, it's dropped into the ocean, and then the second stage ignites. And now you've got a much smaller mass that you're trying to move. All right, so congratulations. You're now rocket scientists. You've heard about Kepler's law. You've heard about the rocket equation. You could even do this at home with a couple of, with a pair of roller skates or a skateboard and a couple of fire extinguisher. It's the same principle. You're throwing mass at a high velocity out the back of your system in order to move you forward out of the front of your system. But please don't tell your parents or your teachers that I told you to do this. Okay, so now that you're rocket scientists, maybe you actually want to get a job as a rocket scientist. So that's a little bit harder. What should you do if you want to be a rocket scientist? I would say take classes in physics and math, chemistry if you're very interested in the types of chemical reactions that allow you to both get into space and also to maneuver around in space. And then if you go to college, study physics, math, chemistry, engineering. There are a lot of disciplines needed. I talked earlier about the fact that you need solar cells. So you need people who are electronics or electrical engineers. You have batteries. So you need people who understand batteries. You've got orbital dynamics, like I study a lot of. You have structural mechanics to make sure that when you're put these satellites on top of a rocket, and launch them into space, they don't shake apart from all of the vibration that occurs if that's just a normal part of launch. And everything, software and software programming. Software at this point, I think, is probably the most complex subsystem of every satellite we launch. We definitely need people to do that sort of thing. While you're in college, and even now, look for internships, hands-on work, your robotics club. My kids participate in robotics clubs too. Those are excellent opportunities to figure out how to build things, how to solve these hard problems that are universal, no matter whether you're building a robot in your robotics class or whether you're building a satellite to go into space. But you also need some things that aren't on a lot of aerospace engineering curriculum. You need creativity, communication, and what I tend to call storytelling. This is again from a Falcon Heavy launch, the first Falcon Heavy launch. Most of you probably saw this. This is the Tesla that Elon Musk launched into space with his Rocket Man inside of it with the Earth in the background. And when we first heard about this particular rocket launch and the fact that he was going to put a Tesla, a lot of people in my organization got kind of mad because we said we could put a few satellites instead of a Tesla into space. But when I saw this and we watched it at work, just like you might watch it at home, I really understood what they were doing here, which is to inspire a whole bunch of people with this image and with what they were seeing, to think about space as a doable thing and to think about space as a possible career. That sort of in storytelling and communication is part of what I think makes a really good rocket scientist or any sort of a scientist or an engineer. You really can't get funding for your idea or get your make your point about something that needs to be fixed unless you know how to communicate, unless you know how to inspire folks, unless you have the creativity to solve the problem in the first place. And, you know, problem solving, critical thinking. This is another picture you may have seen. This is the Earth, and each dot represents a satellite in orbit. Now, this is a little bit of an alarmist picture because each of these dots is much, much bigger than every satellite in orbit. But the main message here is we have a space debris problem. We've been launching satellites for, 60 years or so now. And all those old satellites that don't burn up in the atmosphere and all those rocket bodies that don't re-enter, those that go out to geosynchronous orbit where there's not enough atmosphere to pull them down over time, they all tend to accumulate, and it could get to the point where it's very difficult to navigate around all of these junk satellites or pieces of debris that are out there. In fact, for CloudSat, the mission that I talked about before, I spend a lot of time planning for and maneuvering around debris. And we don't maneuver all that much, but every day I get a report telling me what piece of junk I might run into today. So I need the folks in this room, virtual room, and the folks of your generation to give some thought to how you might solve this problem. And there are hundreds of other problems like it. How will you, what is the interesting problem in science and technology that you want to think about? And rather than being daunted by that, having the sort of the vision and the perseverance to overcome that. And of course, I have a little play on words. This is an illustration of the Perseverance rover, which will be hopefully landing on Mars here in another month or so. And, it's this sort of thing, this thinking outside the box and thinking outside of orbit, that we really need in the rocket science field and in the aerospace engineering field. If you can't dream it, then you can't do it. So I encourage you to, while you're learning your math and science and physics and chemistry, also pay attention to creativity and vision and communication, and stick it out. It's a fun career field to be a part of. It gives you a lot of opportunity to do a really lot of cool things. And I would encourage anybody to pursue this. And that's it. I think that's the end of my talk. I have here, this is the picture of the double rocket landing from the STP-2 mission. The SpaceX Falcon Heavy has a big rocket in the middle and two smaller rockets on the side. And after these two smaller rockets finish burning up their fuel, to lighten the rest of the mass, they separate from the side of the rocket and they actually come down and land on Earth. And great example of the vision and the technical problem solving of a really difficult problem that's brought us kind of a really cool launch. So, all right, let's see if I can make this so I can actually see, and then I will be quiet and let Mr. Bigler and the rest of your folks here see if you want to ask questions or what happens now that my talk is done.
Okay, so thank you, Barbara. That was amazing. I'm going to stop sharing my screen there. Somehow I shared my email by accident, but anyway, so yeah, thank you. That was a really fun talk. So I think what I want to do is just open the floor up to anyone who has questions, students, teachers, whomever. Go for it. Okay, so Ms. Herrera, we should unmute you. There you go.
Hi. Hi, thank you for that talk. It was great. One question I had a little while back when you were showing pictures from the satellite could go through the cloud layer. I didn't know they could do that. I was in the impression I had gone to a talk about the Globe Observer and how out in Montana, they were taking pictures for citizen science below the cloud level so that the satellite could match up the data. So I had the impression that they couldn't see under the cloud. So now I don't understand why we were doing pictures under the cloud layer to help the satellite.
Yeah, no, and I'm familiar with the Globe Observer app, and in fact, my middle child used it, and in fact, we use it. So CloudSat can see through clouds, you know, from the tops to the bottoms, but it can't see through every cloud everywhere. And it's also fairly unusual in that most satellites can't. Most satellites can only see the top layers of the clouds. So CloudSat only flies over the same point of the Earth once every 16 days, actually. You know, the image I showed before, how you can cover the entire Earth in one day, that's actually a little bit of a misnomer because it requires a field of view that's really, really large. And in reality, CloudSat's field of view is much, much smaller. So the citizen science for looking at clouds and comparing them to on-orbit satellites is useful for multiple reasons. One of which is we can't see every cloud at every time, or we can't see every part of the sky at every time of the day. But the second and equally important is that we don't really know that what we're measuring on the satellites is correct. Somehow you've got to compare it to actual observations on the Earth to say, yeah, well, when I thought that there were low clouds here, there really were low clouds here, and look, we can see them on the Earth. And it helps you do the same sort of science that says, well, when I see this radar return, which is nothing but a number on board the satellite, what it really means is a low-lying layer of clouds that may or may not produce rain. And that's true not just for clouds, but also aerosols in the atmosphere. The color of the sky can tell you a lot about the types of particulate matter, aerosols, and so forth in the sky, and we can compare that to measurements from satellites and make sure that they match, and make sure that we know what it really means to see this sort of data number on a satellite. So it's 100% necessary. The fact that CloudSat can look through and see water droplets all the way to the ground is very nice, but we still need people to look up from the Earth and tell us what they're seeing from there.
Thank you.
Okay, other questions? Okay, so we have one in the chat. Barbara, can you see the chat, or should I read it?
Nope, I can see it. And the question for those who aren't seeing the chat is, the cubes they are sending into space, I saw a camera in it. What's the purpose of that? If that is a functioning camera, how does it keep itself stable? So the purpose of the camera is to take pictures, surprisingly enough. But there are a lot of different purposes for taking pictures. A lot of the satellites that I've been talking about take pictures of the Earth, and that helps us from everything from watching how crops are growing on land, to how soil erosion is happening, to how clouds form and develop, and so forth. But some satellites take pictures of space to help us figure out, for example, all those pieces of debris that are out there. Where are they? Where are they going? Do I have to worry about them? And some cameras on satellites are actually used as part of the satellite's navigation system, and it literally does stellar navigation, just like old sailors here, and takes pictures of the stars to help point the satellite in the right direction. It's a tricky problem sometimes to keep cameras stable. Most cameras like to be at a very low temperature, so space is pretty darn cold. On the other hand, it's also pretty darn hot, especially if you are a camera in direct sunlight in a vacuum where you've got no air to cool yourself down. So a lot of another discipline that's needed a lot in satellite engineering is thermal engineering and thermodynamics. And so they have designed a lot of systems both for keeping the camera cool and keeping the camera warm if necessary. And as far as keeping the camera steady so that you can take a picture, that's where this navigation and what we call attitude control system helps you out. And so there are essentially, a lot of satellites have big flywheels, like big gyroscopes in them. And those gyroscopes, like if you try to push a gyroscope, it takes a lot of force. Those gyroscopes help keep the satellite stable so it can take a picture and not blur the image. Did that answer your question?
Looks like. Okay, so now Zachary has his hand up, so go ahead.
What are some good like classes you might want to take in high school to get a job in rocket science?
Yep. Well, like I said, physics is very, very important. Math is very important. If you have the opportunity to take calculus, that's a very good thing to do. You'll get that in college, but you can also take it in high school. And chemistry can be important for, like I said, the actual propulsion side. A lot of the rocket fuel that we make, we've burned everything from kerosene, actually, the same sort of stuff that you would use in a kerosene lamp, up to these new propellants that are what we call green propellants, which are a little bit more stable and a little less hazardous to the environment. So chemistry can help with that. But like I said, physics and math, but also, English and communications makes a big difference, especially as an engineer when you're trying to sell your idea or communicate your idea, or get other people on board with your idea. And computer science, if that's an option for you, is also very good. There's a lot of different ways to be a part of the space program and satellites and rockets and aerospace engineering, but they all rely to some extent on math and physics.
Thank you.
Okay, so another couple questions in the chat.
All right, I see one that said, a question about how you decided you were going to pursue a career in astronomy. You mentioned that you became interested in space after the Challenger. After that, how did you know you were going to major in astronomy and dedicate your life to it? Well, I didn't. When I was in 8th grade, I was pretty sure I wanted to go into aerospace engineering. And then when I was in high school, I knew I wanted to go into engineering. I liked the math. I liked the problem solving. I wasn't sure if it was going to be aerospace engineering. But as I kind of learned more about physics and more about biology and more about chemistry, I really kind of gravitated toward the physics. And I was really highly inspired by space and the space program. Like a lot of people, I wanted to be an astronaut. Maybe I'll still someday be an astronaut. I kind of doubt it, but I'm hopeful. That's where I kind of drew my inspiration for it. So I chose to major in aerospace engineering. It was kind of hard to get a job in aerospace engineering when I graduated, but I had gotten an ROTC scholarship to college. So I joined essentially the Air Force paid for my college education, and then I went on active duty. And they did a good job of keeping me in the field of aerospace engineering and giving me the opportunity to do rockets and rocket science for a career. So, it's probably like a lot of people, you gravitate toward what interests you, and then you try to figure out how you can do that for the rest of your life so that you can always enjoy what you do. Let's see, someone asked, what's your thoughts about investments made into space exploration? Is private investment a good alternative? I think it's absolutely a great alternative. And a lot of folks in my business are very interested. Even my company, which isn't a commercially traded or essentially it's almost like a public company. It's a not-for-profit company. But we spend a lot of time talking to the government and to NASA about how commercial companies can do what you need to do. So commercial companies do a lot of the Earth imaging for us these days. You can see them all on, even Google Maps, or a company called Planet, used to be called Planet Labs. They sell commercial pictures of the Earth. And obviously the commercial company SpaceX is what's launching our astronauts to the ISS. The creativity and the entrepreneurship and the ability to solve problems in the commercial industry is really unmatched. And, the government tends to be stuck in its ways and tends to not think outside the box. And we really rely on commercial industry to do that. So I am hoping that that we get to the point where I can get a plane ticket and go to the moon, or get the plane ticket and go to orbit. And I expect by the time your kids are my age, that'll be something that we're doing.
Cool. Anyone else have any questions or thoughts or anything?